In this video, we're going to begin to discuss the concept of normalization, sort of a way to design databases. We'll talk about the first normal form. There are a sequence of normal forms. We'll talk about the first normal form and begin to talk about moving to the second normal form, and we'll talk about some anomalies. Okay. Okay, so we're going to start with normalization, and it's a procedure to sort of help us design relational databases, and with the to give us some assurance that like each individual little piece of data that we can get at it with when we query that our relationships are modeled correctly, and then we have as little redundancy as possible. So redundancy being like repeated information. Okay. So if we were ER modeling, then we sort of come into the situation and describe from a sort of a top-down approach what we think our entities would be and what their properties would be and what their relationships would be. Um, when we're doing normalization, it's more of a bottom-up approach. We envision some like data that already exists, some sort of like printout of like this is what the data that we're going to have in the database. This is what we expect to get out of the database. Now let's sort of reverse engineer it, sort of so work from the data up. Whereas in ER modeling, you're just thinking generically of the big things and moving down. In normalization, you've got actual some a subset of actual data, and you're sort of imagine how should I break it apart, and you should get at the same place uh, from both approaches, but they sort of complement each other. Okay, so one thing we desire in our results in the resulting database is that each little piece of information should be accessible and identifiable, and um, so we know that like the idea of a relation is realized as a table, and then so a table should have a name, then the columns of the table should correspond to properties, and they should have names, and then each row should be uniquely identifiable by some primary key, and therefore then the table is identifiable, the columns identifiable, the rows identifiable, and then we're drilling down to just an individual cell with a piece of information. Okay, so I'm going to imagine this uh, database about the show The Simpsons. And so I want to be able to get down to a piece of information like Bart. So that is a first name in the character table with a particular ID. And so I can pick out the row and the column in the table and get at that piece of data. Okay. So our first rule is that to be able to identify a unique piece of information, that we should have no multi-valued fields, so that uh, I should not have like each when I get down to tables, each little cell in the table, each intersection of a row and a column should just have one thing in it. So there shouldn't be multiple values in that cell. There should be one thing in that cell. I don't want to have to break it up in any way. I don't want to have to parse that thing. I just want to have it, when I do all that identifying table, column, row, then it should be that individual thing, and I shouldn't have to sort of do any work to break it apart after that. Okay. So imagine I had a table representing uh, information about The Simpsons, and I have some person, Dan Castellaneta, and he voices a bunch of characters. And so I should not have a table that looks like this because that character cell, he voices a lot of characters. So that character cell is multi-valued, and I should not have multi-valued cells. So the first thing we do is we say that we flatten the table so that we are going to do something. We said we didn't want much redundancy, but the first thing we're going to do is sort of introduce some redundancy and then try and get rid of it. So I so our first rule is we don't want multi-valued fields, and so we're going to uh, take that voice actor Dan, and we are going to repeat him, make a row, many rows for him for each individual character. So we are flattening the table. We're taking that multi-valued field that we saw before, and we're going to make a row for each one of those values. And this is known as flattening. So now I have the person's ID and the person's first name and last name, and then each character individually. Okay. So if I've done that, if I've gotten rid of any multi-valued fields, then so I only have single valued field, then I'm said to be in the first normal form. So I'm going to have this again, the sequence of normal forms, which are going to get me uh, closer, get rid of, each one is to get rid of more redundancy. But this one actually introduces redundancy, but it allows us our first key thing that we need is that each piece of data has to be sort of single valued by itself. So just pure querying table, column, row will get us an individual piece of data. Okay. So what has been gained? So a character like Barney Gumble is no longer part of a list, but he's an individual entry. And so if I can say the table and the row and the column, then I have Barney and no, I don't have to break a big long list down and see if he's in the list. It's one piece of information. Okay. But I've introduced redundancy, and I would like to get rid of redundancy in the longer run, but let's just talk about some of the problems of redundancy. These are the so-called data anomalies. Why not just have redundancy? What's the problem with redundancy? Um, and they can make there are storage issues. Like, if you have something that's repeated, then you're sort of, maybe wasting space. We have to figure that out. Are we wasting space? But we assume that would waste a lot of space to have something over and over again. But it also can have issues with the data's integrity, the correctness of the data. So we have this idea of garbage in, garbage out, GIGO, that people talk about in computer science. And so we want our database, what we put into it and what we get out of it, to be correct and to be not just sort of the first time we put it in, but if we make any changes, that those changes uh, propagate throughout and are sort of done once and for all. And okay. So we have the concept of a key that we've talked about before, that each row will be uniquely identified by a key. And so that's going to be important for us in querying because we want to get at a a piece of data. And so that's going to serve the purpose of uniquely identifying a row, but also it's going to come in to help us maintain our relationships, as we'll see. So in the unflattened table, I could just say, oh, Dan had a person ID and then that identified everything. But once I flattened the table, then Dan was repeated. And so Dan's ID is not enough in this new flattened table to uh, be unique. And so we've got to sort of figure out this flattened table that has both the person and the character in it. The person ID is no longer enough. Okay. So we need to think about keys. So one thing you could just do is make a new key. Um, and okay, that can sometimes that's what one does, but sometimes what we're going to do in normalization is start to try to figure out how to break this table into pieces to get rid of the redundancy. If you just introduce a unique key, that solves that problem, but it doesn't really solve the redundancy problem. It just resolves the uniqueness problem. So in normalization, we will look at sort of before we introduce just a whole new, just bringing in this whole new primary key, we will look at what we've got to see how each row is unique. Okay, so the so we have we might want to make a composite key. So we have the person and we also have like the character. So we might need something of the character and something of the person to become unique. Um, then there can be issues like we have this table that was talking about uh, people voicing characters, but then we're also have some ideas in here of there may be people who don't voice a character, like the producers of the show, or there might be a character who really doesn't speak um, and so isn't voiced. Um, and so we're going to introduce this concept of composite key. And so there might be some character information and some real person information combined to make this composite key, but that no part of a key should be null. And so then um, what about what about a producer? What about a character like Maggie Simpson who's not really voiced? Okay. So we're going to ignore it, but it is going to come back and we'll see if it gets resolved as we move through the normalization process. But we see that we to uniquely identify a row, we may need some person information and some character information. And one issue with this is the anomaly problem. So we're thinking eventually we have characters and we have people, and if we try to bring in a person that doesn't voice a character, that's going to cause a problem at this stage. And if we try to bring in a character that is not voiced, that can be a problem. So that can be sort of a chicken and egg problem called the insertion anomaly. That we're our original table had this relationship of a person voicing a character, but now it seems like we need both simultaneously to be able to support this table. So we will that's an issue we have to, will our normalization resolve our insertion anomaly? Similarly, there is a deletion anomaly. We saw that Dan voiced a lot of characters. So if we got rid of Dan, would all his characters sort of go with them? And there are times you might want that. Um, And then there are times you don't want that. So that's a decision one must make in design. But if you have that phenomena occurring and you don't want it, then that would be a deletion anomaly. And then there is an update anomaly. And all these things, insert and delete and update, these are the standard things you do with data other than just querying it. And so each in turn can uh, cause anomalies if we don't set up the database right. So the the insert is when we're bringing somebody in. Are there problems with the order in which it's brought in? Deletion, if we delete something, are we deleting more than we want to delete? And this final one is the update anomaly. What if we change the data? So this guy's got a complicated name and it's easy to misspell. I'm sure I misspelled it, and now I want to update it. Well, if I have the flattened table with his name appearing over and over again, and I want to update it, then I'm going to have to find every place that his name appears and fix it. And so a problem like that of that I might not find all the places and update it everywhere. And so I will end up with inconsistencies in my data and bad data integrity. This is known as the update anomaly. Okay. So here is our flattened table. And now we want to begin to think about the idea of splitting it up and moving toward a person table and a character table, but we don't want to lose the relationship. So we want to take our table and split it up to have more tables and hopefully reduce our redundancy problem, this repeated data problem. So if I re reduce the number of times that Dan's name appears, then if I correct Dan's names, I'll have to fix it in fewer places, ideally fix it in only one place. And so um, we are going to, but we don't want to lose relationships. So what we do is play with our idea of key. And so I'm going to split off character information from person data and but retain the relationship with a foreign key. And then I have to know uh, whether it's a one to many, a many to many, what kind of relationship it is, and that will help me determine where my foreign key goes. But the idea of the foreign key is I'm not going to use Dan's last name as part of ultimately as part of the foreign key because that's something I might update. So I want to keep my foreign key simple so that I can't get rid of all the redundancy. I need some information about the person in the character table. So I need a foreign key, but I want to keep that foreign key simple so that there's no reason to change it. Um, and then the name Dan will only appear once over in the real person table. And so will fix it that one time. I will not change his primary key. And all the characters he voices will have his ID as a foreign key. And that, again, the key, the idea with the keys, one of the ideas with keys is we want them to be simple and we don't want them to have to change. Okay. So if we split this table, we might have, originally we had a table that had both sets of information, people and characters, and then we imagined splitting them to a real person and a character. And the real person had a person ID and the character had a character ID, but then the character table ended up with a person ID as a foreign key. So the relationship is maintained, but we've reduced the redundancy, by making more tables. Okay, so there is some repetition. That real person ID, the person ID will appear repeatedly in many character tables, but that's essential to keep because it maintains the relationship. So we don't want to uh, lose. We can't get rid of all of the repetition because some of that repetition is what provides our relationship. With if we got rid of all uh, repetition, we would lose the relationship. So we need some repetition, but sort of as little as possible, enough to keep the relationship, but enough not to have insert anomalies, update anomalies, delete anomalies. Um, so we want, when we split something up, we have to imagine that we can put it back together again. So that's why I have Humpty Dumpty on this page up there. I need what's called a lossless join property. So I started off in normalization with some table. I'm imagining splitting it into two tables, but I should be able to get the original table back. So I should be able to not lose any data when I join those tables back together when I query. And I should have the uh, any relationship, any constraints I placed on the data, any domains, any limits of things, those should somehow be maintained. Okay, and that's it for this one. More to come. Normalization is a big topic. This is just our start. Thanks for your attention.